Superposition theorem. The principle of superposition is well studied in your physics courses. Examples are the net force in Newton's second law. Here, we say that there's this thing called the resultant or the net force, and it's equal to the sum of the individual forces. That's a superposition of forces. We also have electric fields. Or I should be careful and say the net electric field. Here, we also have the net field felt by an object, which would then be the sum of individual electric fields. And then finally, there's the resultant wave. And the way we typically write the resultant wave is that we then say that the resultant wave is equal to the sum of all of the individual waves. So what we're seeing here is the net or resultant is a single effect. Felt by objects. And not individual entities. The same principle applies to power supplies. But it's different. It's slightly different. So then we have the superposition of power supplies. So I'll talk about the current, but the current, by the way, I could have also said voltage. Through some element and I'm going to say that this current, that through some element, I'm going to say that this current here is I net. Is the algebraic sum of all currents produced independently by each source. In other words, that the net current is then going to be the current produced by source 1. And then if I have a second source, it's going to be produced by source 2. And depending on how many sources are there, it's the combination of all of these sources. But that's not all to the theorem. We have to look at the details. So if I look at the details, it looks something like this. The first thing that you have to do is that to isolate a single source, say source 1, 1 must deactivate all independent sources. You can't do it with dependent sources. All independent sources while keeping source 1 active. So saying this one more time. So that is that we keep source 1 active so that it is the lone source in the circuit. All other sources must be turned off or deactivate so that they do not contribute to the current through the element of interest. So then it comes down to how to deactivate. So to deactivate a source, 1 shorts out voltage sources while opening while opening up current sources. So picture-wise, I mean the following thing. So imagine that I have a voltage source. So we're going to want to take a voltage source and deactivate it. So I imagine that I have a source like this that's connected to some branch in the circuit. And so when I look at this, I see here that I have this source. So I have this circuit. So now I want to deactivate that source. So then I come in and I place a short across this thing. And so what we know here is that shorts have 0 voltage across them. So as a consequence, it removes the source. So then we replace this circuit with the circuit that now looks something like this, where now we only have a short that has 0 voltage. That's how I would replace, how I would deactivate a source. Now, the same thing happens with a current source. So if I want to deactivate, so if I have a current source, and deactivate it, I play the same type of game here. So in this picture, what do I have? Again, I have my circuit. And then here, let me just copy this. So here, I have a current source in here. So this is my current source. And I'll say that this is source 1. And I see that this is connected to this circuit. So now what I do is that now I open the branch. So as I open the branch, I then have this situation where I'm seeing that now I have this guy and I've opened it. So now the current source cannot supply any current to the circuit. So now I can replace with this circuit. And therefore, I've turned off this current source.